Hello, everybody. We are going to do things a little bit differently here starting week 2, just because the long form content, that 30, 45 minutes, is a little bit hard to both produce as well as to watch. So we're going to break things down into smaller, more bite sized pieces. This week, we're going to start talking about the principle of buoyancy. So buoyancy, whenever we hear that word, we immediately think about, think about boats, think about something floating, the duck on the pond, something along those lines. So how does it actually work? So buoyancy is all about the different forces, just like we were saying with the different laws of nature and everything. We talk about how there's always an equal and an opposite force happening, and that's what keeps us in place. Like if we're standing on the ground, the force of gravity plus our mass means that we have a force going directly down towards the ground. The ground exerts the same amount of force back up at us, so that's how we stay level and we don't fall straight through the concrete that we're standing on. Water does something very similar where it's going to exert a force, but it just depends on how much force. It depends a lot on some components like density and volume, and so we're going to take a look at that. So buoyancy, this is the upward force exerted by a fluid material that can be liquid or gas. There are gases that are much more dense than oxygen, so you can have things that actually float on gases. So it's this upward force on an object that is immersed in that fluid. It is governed by the principle known as Archimedes' principle. Archimedes was the super smart dude who lived a long time ago, and he figured this all out. So the Archimedes' principle is that the buoyant force acting on an object that is submerged in a fluid is equal to the weight of the fluid displaced by the object. That's a lot of words. In simpler terms, to calculate the buoyant force is equal to the mass of fluid it displaces. Okay? We find that by using this equation. So it's the P represents density, so the density of the fluid multiplied by the volume of the amount of fluid displaced, multiplied by G, which is our gravity constant, 9.81, 9.8. A lot of times also rounded up to 10 if we're not doing super important math. All right, so this is our equation for buoyancy to know what the force of buoyancy is. Density, this little p right here, is what determines whether an object floats or sinks. All right, in most cases, we're going to be talking about water. So a lot of the times we'll talk about the density of water. So if the density of the object being whatever it is that you're putting into the fluid, is less than the density of the fluid, our object will float. If the density of the object is more than the density of the fluid, the object will sink. This is one of those things a lot of people have heard, fat floats better than muscle. And that has to do with densities. Fat is much less dense when compared to muscle, and water is kind of in between those two. So if you tend to have a lot more fat, you tend to be less dense and therefore float. You're less dense than water, so you float. If you have more muscle on your body, you tend to be denser than water and therefore you sink. That's kind of the real world application, the way to think about this. We also throw, so this little chunk right here, we don't get too deep into this. This is more for physics along the lines of we have a specific object and we want to figure out the weight by using buoyancy. So we'll take a cube and we're like, I wonder how much this cube weighs, but I don't have a scale. I just have this bucket of water. And so then we can drop the cube into the bucket of water, measure how much volume it displaces, do this calculation, and then we can figure out the weight. But what's really more important is kind of relating mass to weight. Oftentimes, we'll use the words mass and weight interchangeably, but it's not 100% accurate. Your weight can change depending on where you are. So, for example, if you're here on Earth, gravity is about those 10 meters per second squared. But if you're on the moon and you step on a scale, there's much less gravity, therefore your weight's going to be different. So weight can fluctuate depending on where you are. Mass is a constant. You always take up the same amount of space no matter where you are. So that's a little nitpicky thing, but if you get asked it, that's the explanation. So if you already have the mass of whatever it is that you're using, you can automatically get the weight. And by weight, I mean the force, like the force in newtons that the person, air quotes, weighs, from that original equation that we talked about in week 1. Force equals mass times acceleration, that Newton's second law. In this case, acceleration being the gravity constant. All right. Additionally, volume, if we have the mass and we have the density, we can calculate volume. So this is more just giving a couple of different equations in order to get to where we need to be when we get asked certain questions. So our practice question, this is the kind of examples that we're going to be seeing. A chiropractic student has a mass of 60 kilograms. So we have a mass of 60 kilograms. When I go through questions like this, I always like to write out the information that I'm given, so that way I know exactly what's going on. So mass equals 60 kg. And an average density of 900 kilograms per meter cubed. So I'm going to say density of our object is equal to 900 kilograms per meters cubed. She claims that she cannot swim. Will she sink or float when going to the beach? Seawater density is, so our density of our fluid is 1,050 kilograms per meters cubed. So what we're looking at, and actually I skipped this step just a little bit, looking up here. Buoyant forces floating, our buoyancy force will equal weight, or our object's density will be less than or equal to, our buoyant force will equal weight, therefore our object density is less than our density of water. Buoyant force is less than the object's weight. For sinking, the buoyancy force is less than the weight, so our object has more dense than the fluid. And just honestly, from that number, I can tell you right now, because she is less dense than water, less dense means that she should float. So right off the bat, she should float. Let's take a look at actually what this professor put in the information. So let's take a look. We can kind of solve through this whole thing. Weight is 600 newtons. The way that she got that was she took mass times force equals mass times acceleration. In this case, acceleration being gravity. So that was 60 multiplied by our gravity constant. They use 10. That equals 600. The buoyant force, if completely submerged, the buoyancy force equals density of the fluid, and then the volume displaced. So we have we have the mass, and we have the density of the person. So mass divided by density, volume equals mass divided by density. Volume equals, our mass is 60 kilograms divided by 900. That gives us the 0.067 meters cubed. This is newtons. And then so we have we use our buoyancy force equation right here. We have the density of the fluid, 1,050, multiplied by the volume of the person, 0.067. That's how much they're going to displace. Multiplied by gravity, which is 10. And that gives us 703.5 newtons. Let me see if I can exactly figure out what this professor is doing here. Oh, that's what she did. Weight is 600 newtons because comparing the weight to the buoyancy force, the weight we were able to, instead of using this equation, we were just able to use the force mass times acceleration. So then we compare 703.5 newtons compared to the 600 newtons that the person weighs. 703.5 is greater than 600. Therefore, she floats by about 17% because it's 17% higher. Is all of this math worth it just to figure out exactly what we knew from the very beginning because it gave us the densities? I don't know. Depends on what the professor is specifically asking you. Now you know how to calculate things properly, and you know how to just tell right off the bat if something is going to sink or if something is going to float. Same thing with this next problem. Is there a buoyant force in the air? Air is treated the same as like a fluid, just much, much less dense. So we consider, it's rather insignificant. So yeah, that is our buoyancy, and we will move on to the next chunk talking about pressures.